Hey guys, we're going to be doing some narration over some writing because apparently this did not actually record anything when I thought it did. So first off, we're going to do some trig identity stuff. And oh man, I'm starting to write. This is crazy. I identified that cosecant of x is the same as 1 over sine of x. And then I recopied the rest of the problem. We're going to be distributing this. So 1 over sine of x times sine of x is equal to 1. And then 1 over sine of x times cosine of x is equal to cosine of x over sine of x, which is 1 plus cotangent of x. Moving on to our next problem. We've got some sum and difference identities, and here we have to identify the alpha and beta in this problem. We have an expanded form, and we just got to figure out which one goes with which. Kind of a straightforward problem, so that's it. For the next thing, we are identifying sine of 15 degrees, and we're going to write that as a difference. We could write that as a sum if you wanted to as well. Here we did sine of 45 minus 30, both in degrees. I'm going to use my sum and difference formula to basically plug this in and evaluate this using unit circle stuff. For the sine of a difference, it's going to be sine cosine minus sine cosine where the angles switch. Plugging that stuff in, we get sine of 45 is square root of 2 over 2. Cosine of 30 is a square root of 3 over 2 minus sine of 30 is going to be a half, and cosine of 45 is going to be the square root of 2 over 2. Doing simplification, we get some square root of 6 minus the square root of 2 all over 4. Bada bing. We're going to do a really similar thing for, and by the way, the one that was selected, they factored the square root of 2 out to make your lives more difficult because whoever designed this hates students. Looking at, I'm assuming number 4 is next because that's a different type of problem and is also one that you need to be able to do. We're given some information, and we're going to use a sum and difference formula again because we like repeating things. This time we're using this sum formula for cosine, and we're given a couple of pieces of information. So something about the sine of alpha equals 4/5. Ooh, I used a highlighter there. That's exciting. And the cosine of beta is equal to 12 over 13. Both of these lie in quadrant 1. That just means that both our x and our y values are going to be positive. I'm going to do some lovely triangle setting up in just a minute, but I'm going to plug in the stuff that I already know. For example, cosine of b and sine of a. Do you like how I switched from Greek to English letters in the middle of the problem? That sounds pretty awesome. Okay, triangle number 1. I bet this is going to have an alpha in it. Wait for it, wait for it. There's an alpha. Phew. And we got 3, 4, 5 right triangle. Hey, I bet both of these are special right triangles. So I subbed in 3/5 for cosine of alpha. That seems lovely. In the other triangle, in bright green, we've got 12 over 13. That's another special right triangle. That's a 5, 12, 13 right triangle. If you didn't know these, you could Pythagorize, and you'd be very happy with your answers. I plug that in, and we get our final value. It's going to be like 36 over 65. Minus 20 over 65, which is going to come out as 16 over 65. Mic drop. We have a sound effect after every problem, especially if I have to wait for myself to finish writing the problem and I keep talking. For number 5, we got a similar thing going on, but instead of a sum and difference identity, we're using a double angle identity to find the cosine of 2 theta, and we're going to use cosine squared minus sine squared of theta, which is equivalent to cosine of 2 theta. Hopefully you remember when we proved this together, but if you don't, it will not hurt you on the final. So cosine squared is going to be, well, cosine is 12 over 13, so I'm going to square that. Sine is going to be 5 over 13, I'm going to square that. I have 144 minus 25 all over 169. That sounds like 119 to me, the positive version, which means that we got C as our answer. Are we doing number 6? I don't know. I'm guessing we are because we're still on this page. But it could also be that I was supposed to move on to the next page and this does not automatically move forward. I am confused, so I'm going to keep talking. Okay, there we move. Now we're moving. I wonder what I said originally in that to fill that space. This is asking us to determine whether or not something is a solution, aka can you plug a value in and find a unit circle value for that. In this case, 4 pi over 3 is in quadrant 3. It's going to be a 60-degree family, so we're looking at a root 3 over 2. And because sine is negative in quadrant 3, because all of our y values are, we have a yes as our answer. Woof! What a problem. Again, I don't know if this is going to continue or just going to kind of pause here. This is awkward. Mr. Butterworth, do you want to say hi?
Aloha.
Mr. Butterworth says hi. I'm going to see if I can see. Okay, similarly, we're going to look at some problems on page 2. We're going to do some Algebra 2 problems that we pretend are precalc problems here, like converting logs and exponentials. Log base 4 of 64 is equal to 3 converts to 4 to the third power is equal to 64. And similarly, if you have the same problem but backwards, you're going to get log base 4 of 64 is equal to 3. Evaluating the expression without using calculator, log base 2 of 4, or as Mr. Butterworth says it, log 4 base 2.
Correct way to say it.
He says it's correct. I say it's correct too. We end up with 2 to the x is equal to 4. That means x has to be 2. We're going to do some expanding and condensing. If we are multiplying inside, it means we're going to add the log expressions because logs are exponents. We're also going to have a power raised to a power that's going to come out front, which means that you're kind of multiplying things there. So we get log base b of y plus 4 log base b of z. But we're going to do 11 next. Or maybe I'll skip 11 because it's boring. Nope, I'm doing 11. So 11 is doing this, but backwards we're condensing. And we've got log base c of x plus log base c of y. And if I'm adding on the outside, it means I'm going to multiply on the inside. Squish them together and you are donezo. Using common logs or natural logs to evaluate things, this is kind of stupid. But if we're looking at this, we're changing base here. Or if you're using a TI-84, you can use the log base function on your calculator. You press the math menu, you go down to where it says log base, and you type this in directly. If you don't have this, or if you have an older calculator, you can do log of the inside over log of the base, and that's changing the base to get to where we need to be. If we are looking at 13 and we're being asked to solve this in terms of natural log, first thing I'm going to do is take the natural log of both sides. We have natural log of h to the 3x is equal to the natural log of 2.3. I'm going to move that 3x down in front by using properties of logs. So we get 3x times ln of 8 is equal to ln of 2.3. I bet I'm going to divide by ln of 8 next. In order to get 3x is equal to ln of 2.3 divided by ln of 8. Let's see if that actually shows up. Oh, look at that. Oh, I divided by the 3 at the same time because I'm clever. And why do 2 steps if you can do 1? Next, we're taking the limit of a function by using direct substitution. After graphing and dealing with this, we talked about that often you can just plug things in, and sometimes it comes out with really nice things, like in these problems where we're plugging in numbers and we're getting values that come out nicely, like in this one, -4. There aren't any funny issues there. Oh, and it sounds like I'm speaking now. Oh no, that was Mr. Butterworth saying that sounds fun. That's even more awkward because that was in the middle of this. So I think we have 3 layers of video now at this one. Continuing with some limit stuff. This time we're plugging in a. And one of the things that's going to happen here is we're going to end up with a weird thing where this limit is potentially a little bit simpler than it looks. Because, this is factorable. And if we factor the top of this, we're going to get a minus 5 and a plus 3 multiplied together as quantities, and the bottom we get a plus 3. I bet we can reduce by canceling out a plus 3, leaving us with a minus 5 as a final answer. For number 17, that's super boring because you're plugging in 0 and you get -5 as an answer. For number 18, we are solving an exponential equation, but we already basically did the same problem on the previous page. I guess we're going to take the problem again, because why not? Take the natural log of both sides, and when you do that, you get ln of 3 to the x plus 8 is equal to ln of 5. We're going to move the x plus 8 down in front. You can either distribute that ln of 3, or you can divide by ln of 3, which is what I do here. Smart choice, Mr. Carlson. And then if I minus 8, I get x by itself, leaving me with ln of 5 over ln of 3 minus 8. Number 19, we get another exponential equation. This is going to be in terms of e. I'm going to use ln again. So ln of e to the 3x is equal to ln of 6. Oh wait, ln of 3 to the of e to the 3x is just 3x. So I get 3x is equal to ln of 6, leaving me with x equals ln of 6 over 3. Am I really going through every single problem? This seems like a delightful waste of time. For number 20, oh good, we are. We're going to do the same thing we did before. Log 17 divided by log pi using common logs. You could do this with ln if you chose, but either way, you end up with the same thing. For number 21, we've got to do some combination of logs. We're condensing. Log base b, these things are being subtracted, so the positives go on top. That's going to be m, pull that 5 from the front up to the top as well, and then n in the bottom. For number 22, we are condensing with some division, and as we do that, we end up getting log base 4 of a fraction with x plus 7 on top and x minus 3 on the bottom. For number 23, we're expanding, and we're going to write this as log base 5 of 7 plus log base 5 of 11, and then minus log base 5 of 13, kind of doing the opposite of what we just did. I'm going to add in a lightsaber so I can talk about things at the same time. That's boring. It used to make noises and stuff. But I think I am past this page now. For number 24, we are expanding yet again. I'm going to bring down my powers, and I'm going to write this in terms of a subtraction since we're dividing on the inside. We get 3 log base 3 of x minus 8 log base 3 of y. And we're done. Evaluating the expression without using a calculator, I'm going to take the log base to some power is equal to 10,000. That happens to be the power of 4 since there are 4 zeros there. Similarly, for number 26, log base 2 of 1/8, 2 to some power is equal to 1/8. That power is negative 3. And again, similarly for number 27, if I've got log base 6 of 1/6, 6 to the x is equal to 1/6, therefore x is equal to negative 1. Converting to log form again, log base 5 of 1 over 125 is equal to negative 3 is going to be what we have here based on our base, exponent, and argument. Converting, we just got 5 to the 3 equals x. All right, moving onward. Again, we're going to plug this in. So tangent 7 pi over 6, I know that's a 30-degree triangle. I'm going to set that up. That's going to be a half 1 and the square root of 3 over 2. Opposite over adjacent is square root 1 half over the square root of 3 over 2. When I divide those out, I get 1 over the square root of 3, which is not looking like that, but if we rationalize that denominator, we get that. For number 31, we are looking at the sine of 4 pi over 3. That's going to be a 60-degree triangle. So when I set that up, we also are in, at this point, quadrant 3. So negative root 3 over 2, and a half negative as the x, but we don't care about that. There's a weird noise in there. I don't really understand, but okay, next page. All right, kiddos, we're going to find the exact value of sine of 2 theta, which is equal to 2 sine theta cosine theta. I like how I just spelled sine with an S. Good on me. Now it looks like S colon N, but that's okay. So for this angle, sine is 3/5, cosine is 4/5. When I multiply all those together, I get 2 times 3 times 4 is 24, and 5 times 5 is 25. And I'm done. For problem 33, let's see if I actually scrolled that one. We're doing sine of a minus b, and for that we're going to use our sum and difference formula. We got to figure out both of these triangles. A is going to be within a 3, 4, 5. It's in quadrant 2, so the x is negative. That's why negative 4 is there. And cosine of beta is 5 over 13, so we got 5 over 13, and I'm getting 12 for the opposite. It's in quadrant 1, so all those are positive. So I know this is going to be sine A cosine B minus cosine A sine B. That's an awesome A there. And when I do that, we end up getting 3 over 5 times, and cosine of B is going to be 5 over 13, minus, and then we got negative 4 over 5, and then the other one we're going to get 12 over 13. When I combine those, I'm going to have 65 on the bottom, and it's going to be 15 minus negative 48, which should be 63 over 65. For number 34, is that what we're doing? Okay, so we're going to identify these as A and B. And A and B, this is going to be the sum of, the difference of cosine. And we get 2 pi over 9 minus pi over 18, which is 4 pi over 18 minus pi over 18, which turns out to be 3 pi over 18, which happens to be pi over 6. So cosine of pi over 6 is what that really is equal to. For number 35, we're trying to complete the identity. This is another sum and difference one. Oh, we're skipping this one. Yay! We're skipping down to 37. Since sine squared plus cosine squared is 1, that's an identity we need to use. And then we get 1 plus tangent squared is equal to secant squared. That's a second identity. This is a double Pythagorean identity problem. On to the next page where we get a bunch of limits going on. First off, we got the limit of x to the 4th minus 1 over x minus 1. I'd like you to notice that if you try to take this algebraically just by plugging in 1 and 1, you're going to end up getting 0 over 0. But if we factor this, something better is going to come out of this. It's the difference of two squares on the top. So that's going to be x squared and plus and minus 1. I'm going to have to factor the top again to get x squared plus 1, x plus 1, x minus 1. All over x minus 1. At that point, our x minus 1s cancel out. You could have also done that with long division, but that would have been a bit of a force, as you guys like to say. Now, when I plug in 1, I get 1 plus 1 times 1 plus 1, which is 4. For number 40, if I plug in 4, I get 0 over 0, which means the limit might exist. So when we factor that into x plus 4, x minus 4 over x minus 4, we find out that the x minus 4's cancel out, leaving with just x plus 4. The limit of x plus 4, as x approaches 4, 4 plus 4 is 8. Number 41 is exactly the same, so let's skip to 42, limit from a graph. The limit is x approaches 1. Well, from the left, the limit has a height of 1, and from the right, the limit has a height of 2. Since it's different, the limit does not exist. For 43, the limit is x approaches 0. From the left, we're approaching a height of 0. And from the right, we're approaching a height of 0. Since the limit is the same on both sides, the limit does exist, and the limit has a value of 0. For number 44, from the left, we're approaching 0. In the x direction, we approach 2 from both sides. There's negative 2, rather. So negative 2 is our limit. For number 45, we've given a piecewise function. We've got to find the limit as x approaches negative 1. From both sides, we're approaching the same value, which is negative 2. Therefore, our limit is negative 2. For 46, we're looking at the limit as x approaches negative 1 from the left. That's that first one. That's this guy here. So from the left, we're approaching negative 2. And from the right, we're approaching negative 7. So negative 2 and negative 7 would be those limits respectively, which is choice C. 2, 0. In polar coordinates, this is r and theta. So a radius of 2 with an angle of 0, that's going to be point C. We're going to have some rapid fire pages going on here because these are really short pages. 4, 3 pi over 4, so that's the fourth ring with an angle of 3 pi over 4. That gives me the point that is at D. For negative 4, negative 3 pi over 4, let's find negative 3 pi over 4 first. That's going to be in the third quadrant. Negative 4 means I go in the opposite direction, which ends up in the first quadrant, which is C. For negative 2, 225, which I'm skipping. Woohoo! So let's look at number 51. So we're looking for another way to represent this point. We know that going around in a circle, we have coterminal angles. That's what this is really asking about. And if I add 2 pi to pi over 3, I end up with 2 pi plus 1 over 3, which is 7 pi over 3 as my angle. Okay, looking at 52, we're given some polar coordinates. We've got to make rectangular coordinates. This is r cosine theta and r sine theta. R cosine of 270, cosine of 270 is 0. That's going to turn out to be 0. And r sine of 270, well, sine of 270 is going to be negative 1. 3 times negative 1 is negative 3. That's the point 0, negative 3. You also could have sketched that and probably gotten that without actually doing the math out. Next up, we got 9 cosine 2 pi over 3. 2 pi over 3 is going to be negative a half. So that's negative 9 over 2. And 9 sine of 2 pi over 3. Sine of 2 pi over 3 is going to be the square root of 3 over 2. That's going to be 9 times the square root of 3 over 2, and you can leave it as that. That happens to be, looks like answer choice D, because I can't see that value. For number 54, are we doing that one or are we skipping it? We're skipping it. Moving on to, it looks like, 55. So we've got to find polar coordinates. We're going to do r squared equals x squared plus y squared. The square root of 200 is 10 times the square root of 2, which is going to be any a or c. And then we've got to find the inverse tangent to get the theta. And inverse tangent of negative 10 over 10, that's going to end up being a 45-degree angle in the second quadrant, which is going to be, in the fourth quadrant, which is going to be the square root of, the 7 pi over 4 or something similar to that. But we've already moved on. Another representation means that, oh, my thing stopped, so that's fine. Basically, we're trying to get this point. The trick here is that this has got to be within this 2 pi, so we can't go just plus 2 pi. So if we're looking at this in terms of, we'd be here, one ring out. Another way to do this would be at an angle of 5 pi over 4 with a radius of negative 1, because you'd be going the opposite direction. Got some more limits going on here. Here we got limits at infinity. And when you've got a limit at infinity, we're tracing this graph and seeing where it goes. It goes to 0. For 61, same thing. We had a limit at infinity. And as you follow this graph to the right, it goes up to infinity. For number 63, we are adding some matrices. If we start off in the top left corner, negative 4 plus 6 gives me 2. That means that only A and D are left in the game. And then if I do another one, 1 plus 2 is 3. That means that only A is left. That has to be the answer, even if I don't actually finish that problem. This is going to be a free response, so you will have to actually add these things together. A minus B, 0 for the first part. That gets rid of 2 answers. One of the answers is stupid because it's only one piece. 0 minus 3 would be negative 3, and we're done. For 66, let's see if I skip this or not. we're doing A minus 2B. In other words, each piece is going to be 1 minus 2 times the second piece. So 1 minus 2 times negative 1 is going to be 3. That has to be either B or D. Then we're going to do negative 3 minus 2 times 3, which is going to be negative 9. We're down to answer choice C. For number 68, we're doing a matrix product. We've got to do the first row times the first column. Negative 1 times negative 2 is 2. 3 times negative 1 is going to be negative 3. When I add those, I get negative 1. You'd repeat the same for each of the 4 elements in that matrix. And since my video is not paused, I'm going to come back to this in just a second. Although it might be nice if I had a stylus, so I'm not writing with my finger. The second one is undefined because those dimensions don't match up. Since we're looking at 68, and 68 is going to be a free response, I'm going to have us re-examine some more of this. So first row times the second column, negative 1 times 0 is 0. 3 times 4 is 12. When I add those together, I get 12. Second row, first column, negative 4 plus negative 2 is negative 6. And then we've got second row times second column, 0 plus 8 is 8. And that would be our final matrix. Which, thankfully, that's the same thing we got in the multiple choice, because that would be awkward. Continuing with some matrix stuff, we are going to do number 70, skip number 70, skip number 70. We're going to multiply these two to figure out if this is the inverse. And for an inverse, we've got to get 1, 0, 0, 1. So if we get this as an answer, we're in good shape. So far we've gotten 10 minus 9 is 1. We got the bottom left is going to be 0. But then if I do the next one, it comes out to not 0. So that means it's not an inverse. For number 74, we're trying to find the inverse of the matrix. We know that we flip our A and D terms. So that becomes 4, negative 1. And we make our B and C terms negative. So B, negative 5 and negative 1. We then multiply by 1 over the determinant. The determinant in this case is going to be negative 4 minus 5, which is 9. And that's our actual answer, which happens to be, if I look carefully, A. Okay, now we're into matrices and systems. First off, we got to write things as systems. This is basically writing coefficient matrices and some kind of an answer. Basically taking the coefficients to make one matrix, making sure that they line up x, y. The answers are going to be in the matrix on the right. And then we have to have multiply by the matrix x, y to make sure that works. For number 77, you're going backwards. And you're basically taking the first column as the x's, the second column as the y's, and the third column as the constants on the other side of the equation, which pretty quickly comes out to a solution, which happens to be B. And I'm writing really slowly. And I'm still writing really slowly. For number 79, you're going to have to do a row operation or operations and write the new matrix. This is probably what you're going to be asked to do on your final instead of having to do a full reduced row echelon form, because this makes a lot more sense to me as far as showing me that you know a skill. So we're doing negative 4 times row 1 plus row 2. Negative 4 times row 1 is going to be negative 12 minus 5 is negative 17. Negative 4 times negative 4 is 16, plus 0 is 16. Negative 4 times 1 is negative 4, plus 1 is negative 3. And then negative 4 plus negative 3 is going to be negative 7. All that looks kind of like a 1, but that should be a 7. Okay, it looks like we're looking at 83 since all the problems on this page are kind of the same. The setup you will be asked to do. So this is going to be writing this as an augmented matrix. That's with the vertical lines instead of the equals and the x and the y to save us a little bit of room. I may also ask you to talk about what the goal of this process is, but you will not be asked to actually solve this on your own on the final, I don't think, unless it's going to be calculator based. And on the TI calculators, if you go into the matrix menu, once you put this matrix in as a 3x4 matrix, you can use RREF, which is called reduced row echelon form, and that will give you the solution to this. For some reason I chose 85 to do, although we've done this like 4 times. And what we're trying to do is to find the, oh no, I just drew on this page. But we're trying to find the inverse, so let's do that anyway. So we're going to switch our A and our D, so it's -3 and 3, make the others -3 and 0, and multiply by 1 over the determinant, which is -9 minus 0, 1 over -9, whichever that comes out to be. Woohoo, the answer page, I made it.